We call it a linear statistical model. Okay, so let's get started. You know, what we've been doing before now, we've been focusing on a way to reveal the true value of a parameter. Okay, and if we want to do that, because of the fact that we don't have resources to study everyone in the population, we normally take a sample, right? And when sample is involved, parameter estimation will be involved. And in parameter estimation, I actually need an estimator. And of course, I walk you through how to figure out an estimator, whether by method of moment or by method of maximum likelihood or through sufficient statistic. You know, you remember when you apply the idea of uh, David Blackwell and Raoult, that we call our Blackwell theorem. Of course, you know, if your estimator is a function of sufficient statistic, of course, we said that's going to be a minimum variance. So before now, you know how we actually put estimator in place, okay? By method of moment, by maximum likelihood, and using the sufficient statistic. But I just wanted to take note of this. What we've been doing before now, we've been focusing on, you know, situation whereby the random variable involved, y1 up to yn, the expected value of that very random variable is equal to a constant. What do I mean by that? What I mean, we've been trying to say that, okay, you know what, expectation of y, okay, expectation of y does not depend on anything but a constant. Okay, you know, expected value of y equal to mu. Okay, we did not relate y, okay, to a particular, you know, another variable or parameter. Okay, assumption has been expected value of y is actually equal to a constant, maybe mu or something. But I'm actually going to say this, that is not realistic, because in the real world, okay, relationship exists. You know, situation where I can actually relate the response variable to a particular explanatory variable, and that is what that's going to be the focus in this chapter. We actually going to be seeking relationship. Okay, now let me tell you this. If I really, if you know, if I want to figure out the average stopping time of an automobile vehicle, okay, you know, the average stopping time depends on the amount of speed that automobile is traveling. Okay, that is one of example of, you know, a variable being related to another variable. So if you want to talk about like maybe the relationship between academic success and maybe the amount of time you read, you study. Of course, I cannot just say your average performance is going to depend on nothing. I'm not going to say average performance depend on a constant. We should be able to relate average performance to maybe the numbers of hours you study, or your intelligent quotient, or some other activity that you do, okay, that secure your academic excellence. So one of the, and that is if we want to do that, so that was why I said in practice, okay, there is possibility that the response variable in question could be related to one explanatory variable or more. Okay, an example, I may want to look at the effect of years of education, okay, on income of a person. Okay, so in that situation, okay, I'm not only focusing on why, Okay, but I'm also going to be focusing on X at the same time. But why is it going to be random? Just like the way we've been doing is random. Why X is not going to be random? It's not going to be random, it's going to be fixed. Okay, so then what is intention? Now, let me tell you this. If we are actually seeking redress, the way we're going to approach that within a statistical framework, we need to specify our model. Okay, I told you the other time, we want to understand our environment. Like here now, we want to understand the true relationship between variables. Okay, now statistician will start by specifying a model, a functional form of a model. Okay, now that very model may do a great job or not. Okay, so which means what we are actually looking for, if you take a look at this, we actually interested in figuring out the G of S. You know, I said why approximately G of S. Okay, why so we now need to identify what that function is going to be in such a way that when I average it, okay, it's going to be equal to G of S. Initially, it is not exactly G of S because when we are specifying our model, it is not possible we specify a model that will give a true characterization of reality. I'm going to say that again. It is not possible that we specify a model that we have a true characterization of reality, and that was what we mean by that. You can see that is not equal. That is not equality. That is like approximately. But we believe on average, the second one now, on average, the estimated model will now be the same as reality. Okay, so why is it that initially the specification of this model, does not give us exact reality? Is because the specification of a model, the way Y is, that very Y, that response variable is contaminated. Contaminated, okay, there's going to be the real function, G of S, that give us the true characterization of reality. There's always going to be a gap. That gap is the error. Okay, which means the way Y is specified, Y is going to be equal to G of S plus the error. And that was the reason why George Boss said, and I quote, if you ask a question on whether a model is true, okay, if you mean a whole truth, then a model is not true. Okay, and that was why he said all models are wrong, but some are useful. All models are wrong, some are useful. I want to believe the reason why he said that is because there's always going to be a random component in our model specification. So when you take a look at G of S, the G of S is actually going to be a deterministic component, while error is going to be the random component. And that is the way the typical statistical model is. Okay, so when I find the expectation of Y, okay, expectation of Y will now give us G of S. We are assuming that on average, error equal to 0. What does that mean in the actual sense? On average, error equal to 0. If I'm looking at the effect of numbers of years of education on income, okay, now, and I said on average, expected value of error equal to 0. You know what that means? It means any other variable or factor other than numbers of years that are have effect on income, we've been able to control that. We believe that their effect is negligible. Okay, that is why we don't capture them in this model. Okay, so if we really want to know how great a statistical model is, if we're able to control the nuisance parameter, the random component, and that is why assumptions in statistical model revolve around the error. if I want to know whether a model is going to do a great job, then if assumptions underlying that settle on the error hold, then the model is going to do a great job. Okay, a model is as good as assumption putting into a model. That's what it means. Okay, now X is going to be called independent variable. Y is going to be called dependent. We also call X, explanatory variable. We also call it predator. We also call Y dependent. We also call it response variable, and some call it outcome variable. Okay, now I'm going to move right now. Now let us see how a typical data set is going to look like. Let me tell you this. When you are using statistical ideology will focus more on the theory. Emphasis is going to be more on the theory. Statistical ideology is about model explanation. Statistical ideology is more about explaining relationship. Machine learning algorithm is about prediction. Okay, there's a difference between when you are pursuing an explanatory goal and when you are pursuing a predictive goal. The two are not the same. Statistical models are very, very good for explanatory goal, like you're trying to figure out relationship. Relationship does not mean prediction. Okay, relationship does not mean prediction. Okay, so but the machine learning, on the other hand, is targeted towards prediction. It doesn't matter if the model is not transparent, provided it gives us the best prediction, we're actually going to be fine. So statistical approach, what I'm trying to say, some of us in scientific community, economy, psychologists, sociologists, statisticians, emphasis is more on the theory. Okay, why we use data in as a supplement, to spice the theory. But the emphasis in machine learning, those who use machine, is on the data. Okay, they use theory in a less formal way. Okay, and that is why in statistics we focus more on the theory. But we now want to look at the behavior of the theory on the data to be able to see. Now, right now, okay, we have a typical data set that we collect from individuals. We collected that based on the numbers of years of education and the income. We are seeking to actually investigate relationship. Okay, now what we're going to do, if we want to look at the relationship, we can actually generate what I call a scatter plot. A scatter plot is a diagrammatical plotting of Y against S. If you take a look at that, okay, now you can see the G of S. Don't forget, we actually want to estimate the target function, which is a model. That's what we want to estimate, believing that the expectation of the target function of the estimate will give us the target function. Okay, now when you take a look at this now, unlike in physics, chemistry, there are some models they will specify that will only be deterministic. I remember Newton law, F equal to ma. Has anybody heard about that? F equal to ma. There's no any error, right? That's deterministic. Okay, F. At times, if we can use a deterministic model with small error, there's no problem. Okay, when you take a look at a situation where force is actually being related to mass and the acceleration, in physics, that is deterministic. Okay, but in statistics, is that when you take a look at statistical models, okay, we're always going to incorporate random components because we acknowledge the fact that there's always going to be a gap between a model and reality. All what we just trying to do is to minimize the gap. Do you know that what I'm seeing right now is telling me that relationship here is not going to be deterministic because of the fact that there's some point are scattered away? Because if it's going to be a deterministic, deterministic is going to imply a perfect relationship. This is not perfect. Okay, If it's going to be perfect and it's going to be a curve, we expect all the point to be on the line. Does that make sense? So you got some point that are scattered away. That's allowed. Okay. So this is the relationship now. So that is a curve. You just generate a scatter plot. That is a preliminary. That's part of preliminary investigation. Okay. Now, whenever we're seeking relationship, we're actually going to use regression analysis. Relationship may be linear or non-linear. Okay. And that was why I said, number one, it will uncover the effects. Statistical models are very good for they are very good for when you are pursuing an explanatory goal. If I want to know the effects of a particular variable on another variable, if I want to know the relationship that exists between them, okay, I can actually use statistical model. Okay, for instance, you can see I may want to look at the effects of gender, okay, experience, education, on income. And maybe my primary variable of interest is gender. Do you know that uh, if you take a look at gender now, okay, maybe male or female, okay, if this is the primary variable of interest, that's going to be categorical. I want to look at the effect of gender on income. If I want to look at the effect of gender on income, that is synonymous with comparing two groups, male and female, comparing the salaries, average salaries of male and female, where I can use a t-test, right? And I can actually use a regression. But do you know that the reason why we cannot conclude on causation, because correlation does not imply causation, because the fact that relationship exists does not mean one causes the other. Okay, if I look at the relationship between sales of ice cream and crime rates, okay, sales of ice cream and crime rate, for example, and if positive relationship exists between them, maybe does that mean uh, more sales of ice cream and more crime rate? No. Okay, because of the fact that the reason why we cannot conclude on causation like that, when I say causation, I mean cause and effect. Why I cannot conclude that is because there could be some other potential variables that are influencing relationship between them that we did not put into consideration. If you want to look at that example now, I want to talk about weather, because people buy more of ice cream maybe during the summer. Okay, and the same thing here. If I want to look at the effect of gender or income, I will have to look at other potential variables that could have effect on income, like the years of education, the experience of workers. Those two are confounding variables. If you don't control them, they will actually, the relationship that we're going to have at the end of the day will be spurious. We don't want to have spurious. Okay. That was why I said after controlling education experience, then I can now ask a question: does one gender earn more on average? Now, you know what I mean? It actually means, take a look at this guy. I'm having two models. Okay. Oh my God. When you take a look at this model, when we're talking about gender, I'm actually going to use binary 0, 1. Okay, maybe I'm going to say 0, maybe for male. Okay, 1 for female, or use one for male, and it doesn't matter, the labeling doesn't matter. So whenever you use that, what we are comparing here, we are comparing in the two, we've actually adjusted and control years of education and experience, while we are comparing the average salaries of male and female. This is going to be okay. This is going to be better compared to just comparing average male and female salary without putting into consideration other factors that could potentially influence the relationship. Does that make sense to you now? And that was why we do multiple linear regression, where we consider other variables, even though the interest is on a particular variable, the interest is on gender, but along the line, we are also incorporating the effect of some variables that could potentially influence that relationship. Now, another thing now is to pursue a prediction. Okay, predicting the value of the response variable. For instance, I actually, the relationship is fantastic and I want to pursue a predictive goal. Then I can, if I know age, gender, pre-existing condition, and so on like that, can I predict the life expectancy? Or if you know your exam grade, exam 1 grade, exam 2 grade, and the homework, can you actually predict the final grade and so on like that? Is there any question? Okay. Now that is second relationship. Now, let me tell you this. Whenever we want to pursue relationship within statistical framework, we actually, our function is going to be parameterized. The same way probability distribution is a function of parameter, right? You know, every probability distribution is a function of parameter. Then your model, okay, it's also going to be a function of parameter. And that is because there's a parameter in it, then that make it parametric model. Parametric model. What we're trying to say, the real relationship, okay, the real functional form is actually going to be approximately that, okay, which means the model we're going to specify, we have some parameters. That's what we mean. And when we talk about parameters, okay, when we talk about parameters, then it now depends. And those parameters will be unknown. If I'm talking about linear regression now, the parameter will be your intercept and the slope, the beta naught and the beta 1. Does that make sense? If I'm actually talking about simple linear regression, you know, where I'm looking at the effect of x on y, there are going to be two parameters. The intercept, beta naught, and the slope needs to be estimated. And you know what? If it is quadratic, because you know, how am I going to know? If I want to have the sense of the relationship, the very first thing I'm going to do is to generate a scatter plot. The scatter plot, you know, when I plot my data and I see that shape, straight line, then I'm actually going to specify a linear regression model. If I see a curve like that, it's going to be a quadratic. Take a look at that. We don't just specify model. We're actually going to have you're going to make a sense of the model if you actually have a diagrammatical plotting. Okay, I needed to take a look at that. Now, the parameters here, we got beta naught, beta 1, beta 2. But here we got beta naught, beta 1. These parameters are unknown and they need to be estimated. Okay, but you know what? The method of estimation I've walked you through before, the method of movement, the method of maximum likelihood, the one through sufficient statistic. But you know what? The one we're going to use here is actually going to be called the method of least square. Least square. Okay, I'm still going to tell you why do we call it least square. Okay, because the least squared, we're actually going to minimize the error. Okay, and the error is a gap, it's either I got negative error or positive error. If I really want to prove to the world that error of -2 is the same thing as error of 2, if I want to prove to the world, I can square the 2. When I square -2, that will be 4. When I square 2, that will be 4, which means -2 and +2, they are equidistant to the line. And we are now trying to see, even though we know some points will be deviated away from the line, but we're actually going to have a strong relationship if the points are very close to the line. And that's what we call least square. Does that make sense? Okay, now I want to move right now. You know, what I normally say, statistics is very easy, you know, very simple the moment you understand what is behind the scene. Okay. Now, maybe when I plotted my y against x and I'm seeing that kind of shape, okay, we actually have the name for different kind of shape, the mathematical theory that we have already I know some of you offer some courses in mathematics, and that will give you opportunity to be able to know the name of different shape. Now imagine you plot your data y against x and you have that shape. That's going to be called an exponential model. Okay. And that is the way exponential model is going to look like. Now, I'm actually making here, I'm making a remark, and I said, assuming that the parametric model, you know what we call parametric model now, you got a model, okay, that made up of parameters, that, consists of parameters, okay, it's reasonably close to the truth. Look at that. Your parametric model reasonable close to the truth. Your parametric model can never be exact truth. We acknowledge that in statistics. There's always going to be a gap between whatever model we use. And that was why we conclude model is not reality. It's not equal to reality. But model will give us some picture of reality. Okay, now the estimation of G dots, which means we need to estimate our target function, becomes the estimation of theta. Because at the end of the day, why become estimation of theta? Because on average, expected value of our estimate will actually give us the true value that we're looking for. We've done all of that in this class. Okay, now let's take a look at a step now. If I want to pursue this, okay, if I want to use a statistical, if I want to pursue this in this statistical framework, maybe I want to know what is the relationship between the income and the income of a patient. If a doctor want to know what is the relationship between income of a patient and the numbers of days that patient will stay in an hospital. Okay, we want to see what of the role of income, okay, to that. If I'm seeking that, I'm actually going to start with the specification of my parametric model. My parametric model could be linear, quadratic, exponential. How am I going to know I'm actually going to do plotting, scatter plots? Does that make sense? For me to be able to have a sense of what the functional form is going to be. And that was why I said, ideally, the model is complex enough so that it can capture potentially complicated relationship between X and Y being simple enough so that theta can be accurately estimated. Let me tell you this. How do we find ourselves in the middle? We got to make sure the model is complicated enough, and it must not be heavily complicated, because when your model is too complicated, it may be difficult for you to estimate parameters. And that is the reason that will lead us to two main sources of error in statistical. The other time I actually walk you through two main sources of error in hypothesis testing, but generally, when it comes to statistical models, we got two main sources of error that we actually call bias, and variance. Okay, those are the two main sources of error. You know what we want to do? We want to make sure we actually strike a balance between bias and the variance. What do I mean by bias? If I want to estimate this function, we will need to make a simplified assumptions. Bias is any simplified assumption made for our model to be easily estimated. Without making that assumption, there's no moving forward. Does that make sense? I'm going to say that again. A simplified assumptions made in order for our target function to be easily estimated. So that is what we mean by that. But what we don't want is high bias. You know what high bias mean? High bias mean the model you specify is too simple and the mod and the reality is complicated, if you are using a simple model for complicated reality, that model will not dictate signal. That model will not dictate the relationship. Okay? That is situation where you have high bias. We can never rule bias out. The one we want is low bias. We don't want the worst enemy of everyone in scientific community is bias. Okay? Now, so high bias is what we don't want. The high bias is a situation whereby your model is too simple. Maybe you're supposed to use a cubic. You know, I show you different kind of function the other time. Maybe the relation is supposed to be cubic or exponential. You are now using simple linear regression. Then your model will be too simple. You may not be able to capture you know what is, the consequence of that? Underfitting. Your model will underfit. Underfit. And that is not good. Your model will underfit. Okay, now, do you know what we normally do to solve problem of high bias in statistical framework? Well, solving problem of high bias is to make our model complicated. But what of in a situation where the model is more complicated than reality? The model is complicated, the reality is simple, then the model will have high variance. High variance. Okay, high variance actually means your model will perform great with training data, but will perform poorly with unseen data. Does that make sense? You know, when you want to make a prediction, right? You split your data, right, into training and test. Your model will do a great job with the training, but it's going to do a very poor job with the test. You know why? Why your model do a very great job with the training data? Because your model capture noise in addition to signal. Your model capture noise, and when your model capture noise in addition to the signal, then you're actually going to have a problem of overfitting. And that is the reason why machine learning algorithm, because in machine learning, they deal with big data. Okay, there's a lot of variable, a lot of data. They're actually going to have a problem of overfitting, but they have a way to check that out. So what we're actually going to do is to to have a bias variance trade-off. Bias variance trade-off. Being able to secure a low bias and a low variance is what will actually enable us to have accurate parameter estimation. Okay, now after that, then we begin with estimation of parameter. Okay, we begin with estimation of parameter. And in estimating parameter, I told you moving forward, we're going to specify our model is going to look like this. If I'm assuming a straight line, our model is going to look like that. There's going to be a deterministic component and the error. The deterministic component is beta naught plus beta 1s. The random is the error. Okay, believing that expectation of when I take the expectation of both sides and we assume that the expected value of error equal to 0, then we actually are going to have a way to estimate our parameters, which is what I'm going to show you in the next lecture. I'm going to walk you through the method of least square, how we derive the estimate of beta naught and the beta 1. Okay. Now we call this a simple linear regression because we are only using a single predictor. Okay. That's why I call simple linear. It's going to be multiple linear if I have more than one predictor. Okay. And let me also tell you this. Even if you are working with a quadratic or a polynomial, this is still linear. That's still linear. You know why we call it linear? It is because it is linear in parameter. You know, we're actually going to say something linear. It's not going to be linear anymore if I have square root of beta naught or square root of beta 1 or beta 1 raised to power something. But now, right now, it's still linear. Even here, it's still linear here. It's still linear here. Take a look at that. And that was why I said all are simple linear models. Okay, because except that The only thing, you know what we are changing? You know what changed relationship? What actually changing relationship? Okay, give me 1 second. Okay, so what is changing is actually x. You know, s could be s squared. It could be cos s in another model. It could be ln s in another model. If it is not x, okay, it could be something else. Take a look at that. Any question? Any question on that? Okay. Then on the other hand, we got a multiple. Okay. I remember what I work on in my capstone project in Nigeria. Uh, I think that was done in 2006, 7. I did, I look at the effect of exchange rate, inflation rate, and consumer price index on the GDP of Nigeria, like the GDP, the gross domestic product. You know, I look at GDP per capita. You know, the GDP was Y. I got more than one explanatory variables. And because of that, I'm actually going to use a multiple linear regression. And that's what you're seeing here in the model specification. Initially, the specification is going to be beta naught, beta 1x1, beta 2x2, up to depending on the numbers of the numbers of independent variables we have. Initially, the specification will be plus error. But after taking expectation, because the expected value of error is going to be 0, then I'm actually going to have that. So we call it multiple linear regression because the numbers of predator is more than 1. Okay, the numbers of predator is more than 1, and the numbers of variables in general is more than 2. You know, we're talking about simple linear regression. The numbers of variables in general is 2. The response and the predator. Does that make sense? Okay, and they're going to become multiple linear. Okay, provided they are all linear in parameters. Okay, they could be not linear in predator. It doesn't matter, it's still linear. But the moment they are still linear in parameter, we can still call them linear. Okay, so take a look at what I'm trying to say here. Okay, you know, at times I could consider quadratic or even consider a polynomial of degree p. You know, doesn't matter, it's still linear. Okay, so I wanted to take notes of all of that. And at times interaction may be involved. For instance, I'm working on X, okay, and also I'm working on Z, and maybe I'm also want to consider interaction effects. Why do I need to seek for why do I need to investigate interaction in statistical modeling? I'm looking at, let's say for instance, if my Y represent my income and X represent years of education and Z represent gender. Okay. Now we actually going to consider interaction if the effect of X on Y is not consistent. Maybe relationship between X and Y depends on Z. Situation where relationship between X and Y depend on another factor, then we need to incorporate interaction effects. That's what I mean. Go ahead. Okay, I'm trying to say here, this is X is the first variable, Z is the second variable. Does that make sense? So I'm looking at the effect of two variables on Y, and I remember I mentioned, okay, let's say Y is income, and X is years of education, and Z is gender, okay? And maybe we may have a kind of belief that need to be tested. Maybe the behavior, the effect of X on Y is not consistent. If the effect of X on Y depend on Z, then we need to test interaction effects in a model. Okay? Now, that is that. Okay, now then we do interpretation of coefficient. Before we can interpret coefficient, we need to first estimate parameters. The regression parameters, for instance, if you take a look at this guy here, what am I doing? I'm looking at the effect of education, experience on income. Then when I specify multiple linear regression model, it's going to be beta naught, beta 1 experience, and beta 2 education. With what we're going to do on Friday, which we call the method of least square, you're actually going to see how parameters in linear regression model can be estimated. Now here I'm assuming we've already estimated that the beta naught is 20, the beta 1 is 0.7, the beta 2 is 1.2, and the question is, because statistics, when you are using statistical model, there's a lot of transparency. That is what makes statistical model different from machine learning algorithm. Machine learning models are black box models. They do a great job on prediction, but they will never do a great job on explanation because they are not transparent. For a model to do a great job on explanation, need to be interpretable. Statistical models are interpretable. Okay, now how do I interpret all of that? Okay, you know what 20 mean? That's an intercept. That is actually going to be the average income when a particular worker has zero experience and zero education. Does that make sense? When I plug in 0, 0, you know, you did that in high school. Y intercept. That is what that 20 means. Okay. Now, if I want to interpret this now, okay, this actually, this is positive here. This means after controlling years of education, okay, it is expected that average income is going to increase by 0.7. That is after controlling that. And if I want to interpret the 1.2 here, after controlling experience, okay, or adjusting experience, the years of education contributed on average 1.2 to the income. Does that make sense? Maybe that is the reason why if that guy is positive and significant, because what we're going to be doing in chapter 11, apart from estimating parameters, we're also going to have a way to test hypothesis to see how significant it is. Does that make sense? Okay. And that was why if I want to interpret it, I said fixing education means keeping education at constant or adjusting for that or controlling for that. One extra. So in the actual sense, we're trying to say for every unit increase in experience, a unit increase in experience. After controlling for education, we expect, on average, the average income to go up by 0.7. That's what it means. Okay. And I was like, fixing education, 1 year one extra year of experience increases expected income. You have to mention expected because it's average. Let me tell you another thing. Explanation is based on average. In statistics, we base our explanation on group level, not on individual level. In machine learning, prediction is based on individual level. In statistics, average has a huge weight because we are considering group level. Does that make sense? Okay. Now, our typical data set is actually going to be that. Okay, experience, education, gender. I mean, want to look at that on the income. We can actually build a model on this to be able to see how experience, education, and gender can explain income on average. That's what we do in statistics, on average. Okay, but let me tell you this before I go. I'm going to tell you this. There are two forms of linear regression. We have linear regression in statistics, and there's linear algorithm in machine learning. Does that make sense? Now, when do I use the one in statistics? If I want to isolate effects, if I want to look at relationship, the one in statistics study relationship, and that was why we're actually going to have total variations. We believe there's going to be 100% variation around the response. We actually want to see how much of the variation in the response the model can explain. Okay, when you are pursuing an explanatory goal, then you're actually going to use a statistical linear regression. But if you are pursuing a predictive goal, you're actually going to use linear algorithm in machine learning. Predictive goal, we're working with big data. We got a lot of variables. We don't care about contribution this time around. We don't care whether a variable is significant. We're not interested in that, but we are interested in combination of variables that will give us the best prediction. So there's a difference between the two. Okay, is there any question before I go? That's going to be the end of the material. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.